What's up, everybody? It's a cold, rainy day here at home, so what we're going to do is we're going to look over last Sunday's severe weather event in the Ohio Valley. We'll also check out some of the analysis that I personally put together while preparing a forecast and picking a chase target for this event. First, I want to say if you dig the video, hook me up with a like and a subscribe, and I would appreciate that a lot. From the perspective of the SPC, this is a well-forecast event, especially if you consider all complicating factors. All the reports of severe weather came from within the areas they highlighted for possible severe weather. And furthermore, all the tornadoes reported and confirmed were confined to either the slight or enhanced risk areas. So an awesome job on their part. I also didn't include all of the data that I look at when preparing a forecast or picking a chase target. Instead, I tried to limit it to just a couple charts from the day before, a couple charts from the day of, as well as a post-event analysis I put together to try to analyze why this event played out the way it did, at least in my opinion. What we're going to be looking for in the post-event analysis and looking at why this event played out the way it did has to do with the fact that myself, as well as most of the chasers I know, in line with the SPC, targeted central and southern Indiana. I personally targeted down here and was near Washington County, Indiana, when a series of tornadoes went through there. So it wasn't necessarily a busted chase, but what was fascinating was the greatest clustering of severe reports and tornadoes came from up in Ohio, and while severe weather was expected up there, that wasn't necessarily anticipated. So we're going to be looking at why it played out that way. When preparing a forecast, I use a top-down, ingredients-based approach. That's just the way I was taught to do it by my professors. Different people have different methods. The important thing is pick a method that works for you and stick to it. Don't draw lines just for the sake of drawing lines, but actually visualize the data that line represents as you're plotting it. Look at the observation stations and visualize what they're saying. Is it cloudy? Is it sunny? Is it raining? What are the pressure tendencies at that location? So, pay attention to detail. That's the most critical thing. It's not about the picture you come up with at the end, but doing hand analysis like this really is more about the process. So if you have any questions on how to perform hand analysis or anything like that, feel free to hit me up in a message and we can address that. This 500 millibar chart preceding day would be Saturday the 4th of November. It's 12 Saturday the November, the day before. First thing I notice is an upper low over western Canada, with a shortwave trough moving through the Great Lakes region. The wave would exit the region, and the main player in our severe event was going to be associated with this upper low. You got pretty much zonal flow across the entire U.S., and I overlaid the 300 millibar speed max that was located over the Four Corners region on this chart so I could see where it was in relation to the features at 500 millibars. We'll step into the 19Z surface chart again the day before and look at some of the analysis from it. But the first thing I do when performing surface analysis is, especially in a convective situation, is I want to analyze the moisture field. So I always plot the isodrosotherms first, which are your lines of equal dew point. This light green line corresponds with 60 plus dew points, dark green with 65 plus, and light blue with 70 plus. You can see a broad one with 60 plus dew points already spreading across pretty much to the Ohio River and southward, and then a moisture axis of 65 and 70 plus coming up through Arkansas. You got a surface low with the attendant warm front and a trailing cold front, as well as another surface low to the northwest over the northern tier of the U.S. With another trailing cold front. Moisture wasn't really a concern for this event. As we said, we got a broad warm sector. The source region, which was the Gulf of Mexico, had mid-70s dew points pretty much throughout. There were a few 60s, but pretty much 70 plus dew points, and this surface low had no trouble tapping into that source and advecting the moisture northward. So the moisture box was pretty well checked from the get-go. I also didn't plot isotherms on this chart. I didn't plot too many isobars on this chart because, as I said, for this one, I really just wanted to analyze the moisture field. That was my main concern with this chart. So as we go to the day of, this would be Sunday morning, 12Z. We'll look at 300 millibars. And part of the reason I do a top-down approach is because it lets me see the large-scale processes that are driving a lot of the things going on in the lower levels. So a lot of the time, I'll have, at least in a broad sense, some understanding of what I'm looking for at the surface before I've ever even looked at a surface chart. In this case, you got the upper low now over central Canada, with a split flow regime, northern branch of the jet stream across the northern tier of the U.S. coming in from the Pacific Northwest, and the southern branch of the jet stream crossing in from Southern California over the Four Corners, with a nose at that speed max over the Central Plains. The southern branch was going to be a main driver in our severe event, and the location of that I thought was critical for how things were going to go. We'll step down to the 8-foot chart for the day of 12Z and look at some of the things going on there. As I said, I left out a few charts just for the sake of time. Obviously, the 500 and 700 millibar charts are critical. I do want to say I use the 300 millibar chart for this. Typically during the cool season, I'll use 300 millibars for location of the jet stream, and during the warm season, I'll use 250 or 200 millibars. So in 850 millibars, 12Z, Sunday, the day of. Similar to a surface chart, the first thing I do is add moisture field. And part of the reason for that is you want to assess the quality and depth of the moisture throughout the boundary layer. So if you've got 65-degree dew points at the surface, well, that's good, but you're going to get a vastly different result if all of that moisture is pulled at the surface, as opposed to if that moisture extends throughout a column of the boundary layer. For deep moist convection, you want a deep column of moisture extending throughout the boundary layer. So I think it's highly important to analyze the moisture field both at the surface and up to at least 850 millibars. So again, plot the isodrosotherms first. This green line corresponds with a 10C isodrosotherm, which it's about 50 Fahrenheit. It's about a 50-degree dew point. This light blue is 12C. The a moisture axis that it's extending up through about central southern Illinois. This moisture axis I thought wasn't going to have any trouble advecting over in Indiana. I figured it would probably be somewhere over central Indiana, maybe southwest Ohio near Cincinnati. So that was going to be a key. My philosophy when chasing is, and it's simple. It sounds simple anyway. My philosophy is always to try to put myself in the location where the most favorable ingredients overlap for the longest amount of time. That's always the goal. In this case, this moisture axis I thought was going to be over central Indiana, so the deepest boundary layer moisture is one of the favorable ingredients, so that box I thought was going to be checked. An important reason to use the 850 chart, of course, is to assess the low-level jet. At 12Z, we had about a 40-knot low-level jet in the southwest, and then already tracking over the Ohio Valley, which had a little bit to do with the development of widespread showers across the region. There was so we've got the 850 low up here with the frontal zone at 850 millibars that I just drew in like that. That allows you to assess the slope of the front. So the surface front is down around this, across that way, and at 850 millibars, it's up here, so you can see the slope of the front relative to the surface. The low-level jet, I had a pretty good idea was going to amplify throughout the day. So I didn't think, we already had 40 knots, so I didn't think 50, 60 knot low-level jet was out of the question by any means. The reason I figured it was going to amplify was the northern branch of the jet stream that we looked at earlier came across this. So as it passes over the low-level low pressure, it's going to create divergence, and it's going to actually remove mass from that column. And as it removes mass from that column, as long as the divergence exceeds the convergence you're getting at the surface, as long as you're taking more out of the top than you're putting in at the bottom, your cyclone's going to amplify, which is going to tighten your gradient, which is going to increase your wind fields. We had really short level divergence, so I really didn't see any reason why this low pressure wouldn't amplify, it wouldn't deepen, and if these gradients tighten, we'd see a 50, 60 knot low level jet. And that did in fact end up playing out that way. So what I was interested in is when that gradient tightens and we see amplification of a low level jet, where is that low level jet going to overlap with my moisture axis in the open warm sector? So that was kind of what I was already putting in my mind I was going to watch for throughout the day. So now we'll step down to the surface chart. This is 15Z the day of. Again, first thing, analyze them and see how it's evolved from the day before. So plot out the isodrosotherms. This light runs with 65-degree dew points, and at this time you can already see 65 degrees. There we go. You can see 65 degrees spreading up into kind of western central Indiana, out ahead of the frontal zone, and pretty much the entire warm sector has 60 plus all the way up to northern Ohio. So moisture, definitely check that box. But again, I'm more concerned with where the actual moisture axis of the deepest moisture is going to be located. And using the 850 chart we looked at, I know that it's located somewhere over southern Illinois, and it should advect somewhere over central southern Indiana. Based on the advection regime we were looking at, I was expecting it would be over somewhere over southern and central Indiana. That had a lot to do with the target that I picked. My main concern with what I saw the morning of had to do with these areas here you see shaded in gray. That's actual radar returns as an underlay on this chart. So you can see we're ongoing to be at least ongoing precipitation. So you see plenty of ongoing convection across northern and central Indiana, as well as some post-frontal shafts back in this region. Could be prefrontal, but this front was a little bit weaker than this one was. So ongoing convection across a lot of the region, as well as very widespread thick cloud cover. Pretty much all the observation locations had overcast skies, and if they didn't, at least had mostly cloudy skies. So my main concern was what level of destabilization would we see. I really wasn't that confident we were going to see any breaks in the clouds, so I wasn't positive we were going to see a lot of destabilization. The one positive we had in that situation was SPC mesoanalysis was showing mixed layer CAPE on the order of about 1,000 joules per kilogram, which is only marginally unstable, but this time of year over the Ohio Valley we've seen severe events with less, so that's sufficient. So you've got this area here already. You're starting to see this target come together where you've got sufficient instability. I should point out lapse rates at this time all out ahead of the front were at least 6 C per kilometer. So not steep lapse rates, but again sufficient. So you've got this area of sufficient instability moving into central and southern Indiana, overlapping a pretty deep moisture axis across southern Indiana. So I'm already starting to see that my target's probably going to be somewhere in this region, north of the river, probably south of Indianapolis. I didn't want to go too much farther north because I had real serious concerns about how much overturning the convection in northern Indiana was going to do. I didn't see those storms out. I figured they were going to track into Ohio and intensify at least to some degree. So I wanted to stay probably south of Indianapolis, but maintain my position within the open warm sector somewhere in the moisture axis and instability axis. So, assessing the wind shear at the time, remember we had the very strong upper level flow. It was 110, 120 knots at 300 millibars, 50 plus at 500, even 70 knots at 500 bars in some spots. So we had mostly zonal flow coming across the frontal zone with up to 70 knots of deep layer shear. one of the important things to look at is your shear, the orientation of your shear relative to your boundary. If you've got shear that runs parallel to your boundary, you're going to tend to see storms that hang out in the zone of ascent right along the frontal zone, and they're going to do what I call, they're going to zipper they're going to zipper down the boundary. So you're going to end up with sorry for that. You're going to end up with a linear mode of storms relatively quickly. If your wind profiles are completely perpendicular to the front, you're going to see storms that are going to develop and they're going to move away from the zone of ascent very quickly. Now, you might be able to see some severe storm development initially, but they're going to, at some point, even as they cross the open warm sector, at some point they're going to lose the enhanced ascent along the boundary, and unless they can sustain themselves in that environment, they're going to lose that ascent and they're going to die. So I like the deep layer flow that is at about a 45-degree angle to the boundary, and that's almost exactly what we saw. That's going to allow storms to hang out over the open warm sector, but also be close enough to the zone of ascent to take advantage of that lift and hopefully sustain. And again, 70 knots of deep layer shear is more than enough to help storm updrafts tilt and not choke themselves out. One concern I had was if it would be too much shear. That shear could be much too strong, and you can in fact sometimes see storms that will shear out, and it'll just blow the tops right off of them and they can never get organized. But the fact that we saw some development early on with similar shear profiles led me to believe that we would see storms maintained, but that's always a concern when you get shear profiles that are that strong. So we've already got, just looking at the charts we've looked at, you've got stability axis across central southern Indiana with deep boundary layer moisture overlapping that, stronger coming in from the west overlapping that. Our boundary is going to provide strong focused descent, so we've got moisture, instability, shear, and lift. We've basically created a supercell environment just looking at a couple observation charts. Obviously there's more that goes into supercells than just those things, but you've at least created a potential severe storm environment just looking at a couple observation charts. Now let's talk tornado potential. We mentioned the low-level jet, which did in fact amplify, and we did see 50-plus knot wind fields at 850 millibars. So we've got this low-level jet screaming in from the southwest, pretty much right over the top of our moisture and instability axis, or axes. So what that did was it helped enhance the storm relative helicity, for one thing. At the time of this chart, 0 to 1 SRH was about 230 meters squared per second square. And that was with the weaker low-level jet. So as it increased, that 0 to 1 SRH is only going to go up. And 230 is sufficient for low-level rotation. Now, it takes more than just helicity for tornadogenesis. You've got to have something to help bring the horizontal rotation to the surface. You have something to tilt it and bring it down, but it's a start. So as we see the low-level jet increase, we're going to see 0 to 1 SRH get to 300, maybe even 400 meters squared per second squared. So my target's already pretty much laid out somewhere in this region. I pretty well know that I want to be somewhere in there because that seems to be where the greatest overlap of ingredients is. So at this point it just comes down to fine-tuning exactly where to go. Basically, I chose the area I chose because it's where the overlap was, but it also allowed me to play a little bit farther south simply to stay away from the ongoing convection. I didn't want to tangle with that. I thought that was going to really hurt the instability a lot, so I didn't want to mess with that. So really, I just chose a southern area in the area I thought had the greatest overlap of ingredients. It was also a little bit farther out in the open warm sector, and I was anticipating that surface winds would back a little bit more throughout the day as the surface low tightened up. I should point out a few things that we were looking at and discussing that were questions and also concerns. One was, what was the instability going to look like? And looking at model guidance, I thought the HRRR and the HRRRX were more in line with what we were going to see. The NAM3 was suggesting mixed layer CAPE over 2,000 joules per kilogram, and a lot of times the NAM likes to overdo moisture and instability. So even with the nested grid model, I still was thinking that the HRRR was going to be much more in line with what we were going to see, and in fact it was. I didn't figure we were going to see much more than we were already seeing. Another thing was, with the strong wind fields we were looking at storm motion that was going to be pretty quick. Using the bunkers method, we had right movers were plotted to move at over 30 knots. Left movers were progged to move at over 50 knots. So it's the kind of storms that if you're not on them quick and you're out ahead of them, they're going to fly right by you. You're never going to see them. So that was a concern. That was something to keep in the back of your mind going into this. Was just to be ready for that and plan ahead so you could try to stay out ahead of the storms. Another thing was, I anticipated there to be much stronger capping. I thought there would be a lot stronger capping across the region. Now there was, due to convective overturning and cloud cover, there wasn't very strong destabilization, but I thought there would be a stronger capping inversion in play. Instead, we saw almost no capping across the warm sector, at least not substantial. And what that does is it can greatly affect the storm mode that you get. So if we had stronger capping in play, that's going to suppress initiation in several areas, and you're going to get storms. You get a storm pipe in one place, and then you get another storm pipe in another place. With a lack of capping in place, it was basically a free-for-all all across the frontal zone. So you had storms that were just developing all over the place, and it can very quickly lead to a more upscale storm mode, as opposed to the discrete storms that we were anticipating. As a matter of fact, the only tornado we saw that was more classic, it was a more classic supercell tornado that day, was one of the very first storms that developed, which is actually this one over southern Illinois, as it tracked into southern Indiana. That storm was more of a classic supercell at the time, and it did produce a tornado for a short period of time. And then as it crossed towards Ohio, we actually had the dilemma where we had to choose whether to stick with that storm, which had already produced once, or to go back towards our initial target and see if we got more development as the stronger ascent moved through the area. We did in fact choose to go back west. I didn't like the idea of following a storm too far out into the open warm sector. I didn't like that idea. I thought the more favorable environment was back to the west. It wasn't entirely wrong, although as you go farther north into Ohio, you did see some things go crazy, including I think an EF2 that touched down in Salina, Ohio, and unfortunately it did some damage and did lead to a few injuries. So there's just a few things that I was looking at leading into this event. Just using observation charts, as I said, during an actual forecast scenario, I'm looking at a lot more than just a couple charts, but that's pretty much my thinking that led me to the decisions that I made for this event. I do want to point out one more thing I left out regarding frontal placement. If you're doing analysis on a surface chart, or any chart for that matter, it's very important to accurately place the fronts. It's not going to do any good if the cold front's here and you plot it back here. So, for this chart, I did plot out the isotherms. I use a 4-degree interval. Instead, a lot of people use a 5-degree interval for their isotherms. I use 4. The reason I do that is because somebody pointed out to me once that if you have to, say you're plotting every 4 degrees, if you need to get a more detailed look, and you have to cut it in half, and look at use the half of the interval you're using, it's a lot easier to plot isotherms every 4 degrees and switch to 2 degrees than it is to use every 5 degrees and try to do 2.5. So I use a 4 degree, but regardless, it's important to accurately place the front. So use isotherms, look for the gradient, use satellite data, radar data, soundings if you've got soundings in the right proximity, and get the front placed in the right location. It's a key factor, I promise. We're going to look at a couple soundings real quick, and then we'll look at a post-event. Normally, I'm using Sharpie, by the way. The program I'm using here is the Python version of Sharp. It's similar to what they use at the weather centers. It's open source. You can download it and install it. So if you're interested in it, it's definitely worth having. A lot of the model sites use Sharpie to power their click and point soundings. So it's nice to have the source if you're into that. Normally, when doing sounding analysis, I'll look at soundings all across the warm sector, as well as along the boundary if I can do it, as well as behind the boundary, so I can assess different characteristics. For this, what I did was I just loaded 2 warm sector soundings, one in Lincoln, Illinois, one in Wilmington, Ohio, to kind of look at the characteristics throughout the vertical in the environment. So, see pretty similar profiles, a little bit more dry air intrusion in Wilmington, which is the purple line in the background, the purple lines. So you got a little bit more dry air above 700 millibars, but overall similar profiles. There was a little bit stronger moisture advection to the west, which correlates with Lincoln having stronger moisture readings on the sounding, but similar profiles. There was in fact a capping inversion at about 700 millibars, but not to the extent we thought it was going to be, and it seemed that air parcels really had no problem breaking over that. At the surface, you still see somewhat of inversion, but that's more of an isothermal inversion as opposed to an actual typical capping inversion. So not really doing much in the way of preventing convection. One of the things I look at is the depth of the boundary layer moisture relative to the depth of the circulation along the frontal boundary. So what I'm talking about is, you look over here and you see 10 C dew points up to over 850 millibars. So you got 10 C dew points up to about there. I would load up a sounding for this. I'm not going to load it up. I'll just show you for this right now. But the depth of the circulation along the cold front was somewhere in this range. So the depth of your moisture exceeds the circulation along the cold front. In short, that's good for sustained convection. So that's one of the things I look at. And obviously, you assess all your parameters and kind of analyze what they represent relating to the environment. Low-level relapse rates were very low, but they're still, that's misleading because they're still showing the effects of radiational cooling from the night before. Typically, I would modify the sounding with the actual observed temperature at whatever time I'm looking at the sounding to try to get a more realistic representation. Last thing, we'll look at the hodograph, which obviously is a very critical point of analysis. So what you see, pretty favorable hodographs, strong curvature in the low levels, relatively straight aloft, both sites showing a pretty similar thing. Strong curvature in the low levels, straight aloft, so you get that distinct sickle shape. You like to see surface winds backed a little bit more to be more southerly or southeasterly, but in any case, you know, it is what it is. You got to work with what you got, not what you want. So you got sickle-shaped hodographs. They're long. I did think we would see some enhancement and enlargement of the hodograph because I did think surface winds would back a little bit more than they did. But in any case, somewhat favorable hodographs. One of the things you can do with Sharpie is you can plot out the boundary motion relative to what you're looking at. So we had east-southeast at about 21 knots, so it's going to be roughly that right there. This allows you to see what the winds are like at different levels relative to the boundary. This lets you assess the likelihood that storms will hang out along the boundary, leave the boundary completely, cross the warm sector and leave the zone of ascent, or perhaps if most of your photograph falls behind it, then you might see storms that will actually develop along the front and then be undercut by the front. And obviously if you get a storm that gets undercut by the front, you're going to lose a lot of the ascent, you're going to lose the favorable thermodynamics. So that'll let you assess things like that. We were already seeing STP values up to about 2 across Illinois at this time, by the way. So that was something worth looking at. Last thing with the sounding, and then we'll look at the post-event analysis, and then we'll wrap this thing up. Storm relative winds. Environmental wind obviously is important, but I think that it's much more important to look at storm relative winds. So that's just the wind fields from the perspective of the storm itself. It allows you to assess the characteristics of the inflow, anvil level winds, all of that stuff. It's important to look at the storm relative winds. So you see surface to 1 kilometer, you had storm relative winds out of the east-southeast at about 26 knots is what it was showing. So that was pretty close to what you ended up seeing. You can see everything you're looking at there. But the point I'm trying to make here is it's important to assess the storm relative winds. You know, don't just glance over this. Don't just look at the mean wind, because I mean, if you can have a pretty strong environmental wind, but you can have storm motion that can negate the environmental wind altogether. So it's important to just look at what your storm relative winds look like. So here's a post-event analysis I put together, and I think there were so many tornadoes across northern Ohio when most of us targeted Indiana. This is an SZ observation chart that I put together, and then went back and analyzed this after the fact using observation data from throughout the day. So, just like we were looking at earlier, surface low, a little bit of occlusion taking place, but you got a trailing cold front, northeast to southwest, all the way back into the central plains and even into the western U.S. Broad warm sector extending over most of the eastern U.S. with at least 50 degree dew points across the entire warm sector. And then the area that corresponds with our interest pretty much all fell to 60 plus dew points. So again, moisture sufficient. One of the things was we saw really strong moisture advection. I thought the moisture axis was going to lie somewhere over central Indiana. In fact, it did, but the moisture axis stretched across southern Indiana, central, and went all the way up into northeast Ohio. So that was a big deal. Instability. While instability never really got to be extremely high, you did see was the storms that were initially over Indiana tracked east, and they were able to take advantage of what little diurnal heating there was, which was able to get MLK to about 1,000 joules per kilogram. Those storms were able to cross the open warm sector and take advantage of that little bit of instability, and they were really able to tap into that and re-intensify. So we saw spirulancing into Ohio. No doubt aided by the very strong deep layer. We had the 300 millibar speed max. The nose of that speed max was into western Ohio, about 18Z. So you've got very enhanced deep layer shear over 60 knots. The moisture and instability is there. So pretty much you had moisture, instability, and deep layer shear extending over a much broader area than initially anticipated. You also had favorable wind fields for rotation, aided by the 50 plus knot low level jet that, as we said, it did cross the region we thought it was going to cross, but it was even more extensive than at least I anticipated, and crossed all the way through Ohio as a 50 knot jet. So you had the core of that here in this area. I drew it out somewhat of an ellipse. That's your 50 knot low core at 18Z. That's more than enough shear in the low levels to generate low level rotation. So you've got low level rotation, and you've got favorable wind fields for, of course, mid level rotation, but more importantly, updraft sustainment. So you've got wind shear that supports the potential that storms are going to develop and tilt their updrafts in a way that doesn't choke them out. So now you've got storms with not just a possibility, but a high likelihood that they're going to develop low-level rotation. And we saw this. Almost every storm that we saw this day had at least some rotation throughout. Now all you need is some way to tilt that rotation, which is horizontal. You need some way to tilt that vortex tube and bring it and stretch it down to the ground. Well, we had sufficient low-level lapse rates, about 6C per kilometer. Not steep, but sufficient low-level lapse rates to aid that. And you also had strong storms that were producing pretty efficient rear flank downdrafts. They had some supercell characteristics. While they might not be classic supercells, they had some supercell characteristics. The most important, at least regarding tornado genesis, was they had distinct rear flank downdrafts, which it seems definitely aids the ability to take a horizontal vortex tube, tilt it, and take advantage of the thermodynamics to stretch that to the ground. That's what we saw, and that led to a pretty good number of tornadoes touching down across northern Ohio, where all of these processes overlapped. There were tornadoes in eastern Illinois, southern Indiana. We saw 2 tornadoes in southern Indiana. But there was the EF2 that unfortunately did injuries in Salina, Ohio, and there were several other tornadoes up there that did some damage, and pretty much all the storms that hit up there were severe and made some sort of impact. That's the reasons I think it played out like that. Some of the parameters that we saw aided by the observations I was telling you about, the low-level jet, deep layer shear, etc. Some of the parameters we had 0 SRH that was aided and was able to get over 300 meters squared per second squared. We did see a little bit stronger instability back this way, but we did see severe storms that developed this way, but as far as tornado development, the low-level environment just wasn't quite right. So even though the stronger instability was south over Missouri and then into western Kentucky, it seemed to consistently be trailing just behind the favorable area of low-level wind shear. So you saw that manifest in severe storms, but not necessarily tornadic storms. That's pretty much going to wrap it up. Again, if there's any questions on how to do surface analysis, if you want detail on that, feel free to message me, contact me in any way you can. Hit me up on Twitter, Facebook, whatever the case may be, and ask away. I'll be happy to help you out. We will also be, I will also be uploading another video shortly where we will break down this weekend's weather for 17th, 18th of November. It was looking like we might have a chase day. Now it's not looking like we're going to have a chase day, but that's a very complicated forecast. There's a lot of inconsistencies and uncertainty, so I'll be doing a video on that here shortly, and we'll try to get that uploaded soon and try to address that in more detail. That's going to do it. Thanks for checking this out. Again, contact me if you'd like. I appreciate it. You guys rock on and stay cool.